Hello and welcome. Next couple of lectures we'll be looking at multivariable systems. Until now we have looked at single input single output systems where you got one output to control and you got one input that can be manipulated in order to control the output. Most real processes you want to control multiple things. You got multiple control degrees of freedom, you got multiple valves that you can move. So common problems are multi-input, multi-output. Common control problems are almost always multivariable in nature. And let's look at the simplest multivariable system. The simplest multivariable system would be a 2 by 2 system where you got two control inputs that can be used to control two control outputs. So you've got U1 and U2 as your two control inputs, and you can use this to control, let us say you're controlling a particular process variable using U1. Let's call that process variable Y1, and you're controlling another process variable using U2. Let's call that process variable Y2. So your system, the controller could be decentralized or multivariable in nature. So there are two control inputs and two control outputs to be controlled, and the process is, you've got U1 affects Y1, but then when you change U1 it also affects Y2. U2 sorry U2 affects Y2, but then it also has an effect on Y1. So thus when you change U1, both Y1 and Y2 change, and when you change U2, both Y1 and Y2 change. And we'll put in transfer functions in there, but basically so we'll call this transfer function G11, effect on output 1 of input 1. This would be effect on output 2 of input 1. This would be effect on output 1 of input 2, and this would be effect on output 2 of input 2. Yeah, and if you, this is your process, 2 by 2 process. So this is a very simple multivariable 2 by 2 process. Okay, and if you look at this process, we have Y1 is equal to, if you look at this block diagram, Y1 is equal to G11 U1 plus G12 U2, and Y2 is equal to G21 U1 plus G22 U2. And if you write this in matrix form, what you have is Y1 Y2 is equal to transfer function G11 G12 G21 G22 times U1 U2, or in matrix notation, output vector Y is equal to process transfer function matrix GP times input vector U. So this is a multivariable system process equation. And Now, the simplest control system that we can draw is a decentralized control system. What is a decentralized control system? Decentralized control system. And what is a decentralized control system? We use u1 to control y1, we use u2 to control y2. The changes in u1 are dependent on y1 alone. Movements in y2 do not affect changes in u1. Movement in u2 is affected by y2 alone. Changes in y1 do not affect movement of u2. So u2 acts based only on y2. u1 acts based only on y1. So what we are saying is u1 is equal to gc1, well, let's just call it 1, times error in process variable 1, and u2, and gc1 could be a PID controller. u2 is gc2 times e2, where e1 is equal to y1 set point minus y1, and e2 is equal to y2 set point minus y2. So in other words, if you want to write this in matrix notation, you can write this as u1 u2 is equal to gc1 gc2 cross diagonal terms are 0 times e1 e2, which is the same as saying vector u is equal to controller matrix gc, which is a diagonal matrix with gc1 being the 1 1 element and gc2 being the 2 2 element, and the off diagonal terms being 0 times e, vector e. Now if I substitute this into my process equation, what I then get is, maybe I should continue on the next page. So I've got y is equal to matrix gp times u, and we've got u vector is equal to matrix gc, a diagonal matrix gc, times the error vector e. And if I substitute this into the previous equation, what I get then is y is equal to gp times gc times e, and this is matrix multiplication, so order matters. And e can be replaced by gp gc times the vector y set point minus the vector y. And then if you take the y term to the left hand side, what you will then get is the identity matrix plus gp gc, the matrix, times y is equal to matrix gp gc times y set point. And then what you get is the servo transfer function y is equal to I plus gp gc inverse, the inverse matrix. This is now matrix inversion times GP times GC times y set point. Okay, and when you see this guy out here is actually a matrix of transfer functions. Okay, this is a matrix of transfer functions, and when we invert a matrix, all of the terms are divided by the determinant of that matrix. So the determinant of that matrix occurs, so this matrix, this inverse matrix times GPGC, the inverse matrix will have, for a 2 by 2 system, it will have 4 elements: element 1, element 2, element 3, element 4, and each of these elements you would be having a division by the determinant of that matrix. Let's call this matrix A. I plus GPGC, let's just call, for the sake of convenience, A, the determinant of this matrix A. So this determinant is common to the denominator of all the transfer functions, and because it is common to all the elements of the right hand side matrix, therefore the multivariable closed loop characteristic equation is going to be the determinant of I plus GPGC, its determinant equal to 0. This is the multivariable closed loop characteristic equation. For a 2 by 2 system, we can see what it is. So for our 2 by 2 system, decentralized system, we've got GP is G11, G22, G21, sorry, G12, G22 times GC would be GC1, GC2, the rest is 0. So this is what GPGC is, plus the identity this is I plus GPGC. This guy is going to be, I mean, just see what this guy is going to be. This this into this plus this into this. So this is actually G11 GC1. This into this plus this. So that's G12 GC2, and this guy is going to be G22 GC1, and that guy is going to be G22 GC2, and plus 1 plus 1, so yeah, plus 1 plus 1. So this is the matrix I plus GP GC, and when you want to take the inverse of this matrix, you'll have to divide each of the elements by the determinant. So the determinant of I plus GPGC is going to be 1 plus G11 GC1 times G22 hang on times, let's be consistent, 1 plus G22 GC2 minus, hey, what the hell is this? Did I do it right? नहीं भैया गड़बड़ कर दिए, ये हमको गड़बड़ लग रहा है. G11 times GC1, next is this G11, not G1, G, okay, this is not G22, this is G21, so this guy will be G21. Yeah, okay, so I made a mistake there. Minus G12 G21 GC1 GC2, that's the determinant. And so the characteristic equation is going to be, this guy is equal to 0, but will implies closed loop characteristic equation for the multivariable system is 1 plus G11 GC1 plus G12 G22 GC2 plus G11 G22 GC1 GC2 minus G12 G21 GC1 GC2 is equal to 0. And one can write this further as 1 plus G11 GC1 plus G22 GC2 plus GC1 GC2 into G11 G22 minus G12 G21 is equal to 0. You can see there is this extra term, and this extra term, why does it turn out? Let's look at the block diagram again, and you'll see why it shows up. So I've got these 4 blocks, and I'm using GC1 to control this guy, and I'm using GC2 to control this guy. And let's fill this up. 1 1 2 1 1 2 2 2. This is U1, this is U2, Y1 y2. You can see there is this feedback loop, then there is this feedback loop, but then there's another feedback loop, and that feedback loop is, and I'll draw that feedback loop. There's another loop. Maybe I should use a different color here. How do you use a different color? Pointer options, ink color. What do you want to use? Maybe I'll use the red color. Give me red. So you can see there is also this figure of 8 loop. There is this extra feedback that's occurring in addition to the 2 feedback loops. Arey yaar, ye gadbad ho gayi. So let's use black then. Okay, so we'll use black. So figure of 8 extra feedback loop, that's drawn in red. So it's because of this extra feedback loop that we get this figure of 8. These extra terms are because of that well, actually it is this term which is because of the figure of 8 interaction. I don't know which one it is, but you get the extra term because of G12, G21. If any one of these interaction terms is 0, if G12 is 0 or G21 is 0, so this is the figure of 8 interaction term, the interaction term that ends up there. And therefore, because you got this extra figure of 8 loop, if you tune loop number 1, let's just call this loop 1 for controlling y1, and let's just call this loop 2 for controlling y2. So loop 1, if you control loop 1 and pretend as if loop 2 is not there, if you tune loop 2 and pretend that loop 1 is not there, so let us say you tune loop 1 while loop 2 is open, and you tune loop 2 while loop 1 is open. So if you close loop 1 and run it while loop 2 is open, the system is stable, you get a very nice response, the kinds that we have seen in our simulations. If you open loop 1 and close loop 2 with that kind of tuning, the system will run very well. But if you close both the loops together, then this figure of 8 interaction will kick in, and once this figure of 8 interaction kicks in, the extra feedback will destabilize the system, and you might end up with a system that is highly oscillatory and may even be unstable. So there is this issue of loop interaction. And you've got this option, so you got variable y1 and you got u1, you got variable y2 and you got variable u1. You could have the direct pairing, u1 is controlling y1 and u2 is controlling y2, or you could also have the cross pairing, where y1 is controlled using u2 and y2 is controlled using u1. And now it depends, depending on what pairing you are using, the cross terms here would be different for the 1 1 2 2 pairing versus the 1 2 2 1 pairing. And just like in matrix inversion, when you want to invert matrices, what do? You want to make sure that the matrix is diagonally dominant. The large terms come along the diagonal and the off diagonals are small terms. Similarly, in our process transfer function that we get, G11, G12, G21, G22, we want to make sure that we choose our y1 and y2 such that the these terms are large, the gains are large, these terms are small. So you get a diagonally dominant pairing. If these terms are small, then we know that inverse of that matrix I plus GPGC to the inverse, that would be a well behaved matrix. That inverse would actually be well behaved, stable. Why is it relevant? Because notice this, this negative term will can, I mean, if you remember Ruth array, this will be an expression in polynomial in S. This characteristic equation would be a polynomial in S, and because of this negative term, if G12 G21 is larger than G11 G2, you can end up getting negative coefficients and all other coefficients, some negative coefficients and other coefficients being positive. That means the characteristic equation is unstable. You got some roots on the right half plane. Okay, so therefore we would like a diagonally dominant system. So one of the rules for which pairing to use, is pair in a diagonally dominant manner. Diagonally dominant pairing. What do I mean? Let's not worry about dynamics. Let's just look at steady state. Diagonally dominant pairing. Let's just look at a steady state gains. So let's say I've got y1, y2. y1 is equal to 2 times u1 plus 4 times u2, and y2 is, well, what the hell is y2? 3 times u1 plus 1 times u2. So in matrix form, what we are saying is y1 y2, the relationship is 2 4 3 1 times u1 u2. Now let us say I do the y1 u1 and y2 u2 pairing. In that case, you see the cross terms are larger than the diagonal terms. In this case, this is not a good pairing. The interaction terms are more intense. The cross diagonal terms are larger magnitude than the main diagonal terms. So this is not a good pair. So y1 u1 y2 u2, not a good pairing. It's not a good pairing. Okay. What if I did the pairing the other way? Sorry, y1 y2 will keep the same. What if I did the other pairing? Now y1 is going to be paired with u2, so I'll write u2 first. So this is the same set of equation, except that the pairing has been reversed. In this case, this would be, the columns would be flipped, 4 2 1 3, and now you can see this is diagonally dominant. These are larger and these are small. So this diagonally dominant pairing occurs when we are pairing y1 with u2 and y2 with u1. Because this is diagonally dominant, okay, because diagonally dominant. Yeah. Okay, so this pairing would be better than that pairing just by inspection. Okay, so there is this idea of pairing your outputs with inputs such that your GP matrix is diagonally dominant. Okay, are there other more systematic ways that directly address this issue of interaction? Interaction matrix. So there are two interaction metrics that I want to talk about. Interaction matrix number one is relative gain. Number one is Niederlinsky index. I think that's much more useful than. And number two is the relative gain array. Relative gain array, and we'll talk about both. So let's look at the Niederlinsky index first. I'll just call it Ni, and this is called RGA. So let's look at the Niederlinsky index. Hang on. Let's take a 2 by 2 system, and let's look at only the steady state characteristics. Let's assume there are no integrators, and it's a stable system in the sense that all have finite gains. So stable, so this is K11, K on 2 of 1, K on 1 of 2, K on 2 of 2. And this is what we have. Okay. Unless I show signs, it's assumed that junctions are summations. Okay. Now, let's say I've got PI controller adjusting U1 to hold Y1, and I've got PI controller adjusting U2 to hold Y2. Or let's make it a little bit more primitive, because that will be easier to understand. Let's say what the operator is controlling the process, and what he does is he first moves U1 appropriately so that Y1 is at set point. Now because U1 has been changed, Y2 changes because of the interaction here. Now because Y2 has moved away from set point, therefore the operator then goes about and changes U2 appropriately so that Y2 ends up at set point. But now because U2 has been changed, it has an effect on Y1, and because it has an effect on Y1, then you can make another change in U1, and you keep doing it again and again and again and again until the process ends up at a steady state. Okay, so let us say there is a disturbance, and I'll just take an arbitrary disturbance. It goes to 1. So at time t equal to 0, y1 is at 1. Now in order to, so let's look at u1, and let's look at u2. Well, we'll see. Let's look at u1 first. Now in order to, so y1 has gone to 1. In order to bring it to 0, u1 will have to be minus 1 by k11. I do this, y1 is brought to 0, but then y2 goes to minus K21 by K11. Y2 reaches this value. Now in order to bring this deviated Y2 back to set point, operator would change U2 by how much? He would change U2 by minus K21 by K11 K22. So you can see this signal is just imagine K21 by K11, and so if I change this to minus or plus, hang on, this will have to be plus, sorry, yeah, so this will have to be K21 by K11 K22, and then when I multiply by K22, this will be the exact opposite of that, and they will cancel out, and Y2 will now be back at 0. Okay, but now U2 has deviated, and because U2 has deviated, it will have an effect on Y1, and that effect is going to be K12 times this guy, times this guy actually, K12 times K21 divided by K11 K22. Cycle will repeat, so this guy will now be minus 1 by K11 times K21 K12 divided by K11 K22. This guy would be minus K21 K11 times that guy over there, K21 K12 divided by K11 K22, and this guy would then be plus K21 divided by K11 K22 multiplied by that guy, which is K21 K12 divided by K11 K22, and this guy will create an effect which is and if you keep going ahead and ahead and ahead, this one guy would be so if I look at the changes in U1, it's actually, or U2, let's look at the last column, U2. Changes in U2, they are actually K21 by K11 into K22 times, that's the first iteration, then that's second iteration, it's going to be third iteration, it's going to be and so on and so forth. You can see that this is a geometric progression, and this geometric progression will be u2 will be finite. That means u2 would be stable if this guy would be stable if the ratio is less than 1, if the the geometric progression ratio is less than 1, and so stable if k21 k12 divided by k11 k22 is less than 1. Okay, what that means is k11 k22 minus k, I think should write it the other way, minus k12 k21 divided by k11 k22 is greater than 0. I'll be or let's put it the other way. I think it is better to state it this way: unstable, unbounded if this is greater than 1 or this is less than 0. And what is this guy? What is this guy? If you look at this guy, this is nothing but determinant of k divided by product of the diagonal terms of that matrix k. The matrix k is, that's what it is. For a 2 by 2 system, and you can see that this guy is nothing but this guy. This is called the Netherlinsky index. So the Netherlinsky index is equal to, for a given pairing, determinant of k divided by product kii, and if the ni is less than 0, then the interaction term is so large, the off diagonal interactions are so large that the closed loop system, if you are trying to hold both y1 y2 at set point or y1 y2 yn at set point, the closed loop system is guaranteed integrally unstable. And why are we saying integrally unstable? This integrally implies we are trying to hold all the outputs at their set points. Integrally unstable. So on the other hand, if ni is greater than 0, it does not imply stability. It's a necessary but not sufficient condition, and that is understood. Does not imply guaranteed integral stability. And why is that? Because even if it's a seesaw system, you can always mess up the tuning and get instability. Multivariable system, you got that additional figure of 8 interaction, so stability is not guaranteed. So it's a necessary but not sufficient condition. So just to clarify, let's say we've got a slightly more 3 by 3 system. So you got 3 boys and 3 girls, and we want to make couples. Yeah. So you got u1, u2, u3. You got to check compatibility, right? y1, y2, y3. I think there are 6 possible pairings. The first one is 1 1. Well, we'll say 1 1 2 2 3 3. That's one. Then you could have output 1 with input 2, output 2 with input 1, 3 with 1. Then you could have output 1 with input 3, output 3 with input 1, and you got 2 2. You could also have 1 with 1, output 2 with input 3, output 3 with input 2. 4 ही बने यार. I thought there were 6. Well, are there other pairings? Well, maybe there are just 4 pairings. I don't know. 4C2? No. So this, and this, and this, or you could have this and that, or you could have this and this. Yeah, so there are 4 pairings, 4 possible pairings. Let's say y1, y2, y3, the input output steady state relationship is this guy. So for this pairing, the relationship is here, and therefore the Niederlinsky index would be the determinant of this matrix divided by k11, k22, k3, the terms that come on the main diagonal. Let's take some other pairing. I don't know. Maybe we'll take this pairing. Okay. In this case, what we want to do is we have y1, y2, and y3 as before is equal to, you'll have u1, but then u1, u3, u2, u1, u3, u2. That's the pairing that we are looking at. And for this pairing, so the first column would remain the same, k11, k21, k31. Column 3, 2 and 3 will be flipped, will be exchanged. So it would be k13, k12, k23, k22, k33, and k32. You see now, the Niederlinsky index would be the determinant of this matrix divided by the product of the diagonal terms, which is k11, k23, k32. Do you see? Because we have exchanged a column, the determinant will flip a sign. And what will happen to pi? What will happen to the product of the terms? We'll have to see. So the point is, for every pairing, the K matrix is corresponding to that pairing, and so what occurs on the main diagonal varies from pairing to pairing. And you calculate the Niederlinsky index as, to clarify, you calculate it as determinant of the matrix K corresponding to that pairing, corresponding to that pairing, divided by product of KII. This is also corresponding to that pairing. Okay, and therefore if you got, for example, 4 pairings, you will see that the diagonally dominant pairings have a Netherlinsky index that is greater than 0, whereas the diagonally non-dominant pairings have a Netherlinsky index that is less than 1. So those that have a Netherlinsky index less than 0, sorry, less than 0, greater than 0. So those that have a Netherlinsky index less than 0 are guaranteed unstable, rejected. Those pairings are out of the window, because those pairings are never going to give you integral stability. Okay, that's number 1. So much about Netherlinsky index. Now let's talk about the relative gain array. Relative gain array. Now what is the relative gain? The relative gain lambda, if you are pairing the ith output with the jth input. So there are, let us say, a square system, so there are n outputs, y1, y2 to yn, and there are n inputs, u1, u2 to un, and I indexes the outputs, j indexes the inputs. Okay, so the relative gain lambda ij by definition is change in the output I per unit change in the input j, all other u's constant. What is held constant is uk not equal to j is constant. All other process inputs are constant, divided by dou yi by dou uj, and this time what we are doing is all other outputs are constant. Yk not equal to I are held constant. So in plain English, this means all other inputs constant, and in plain English what this means is all other outputs constant. So this is the relative gain array, and what this means is the relative gain array is, in a sense, the gain that loop sees, the gain that this controller would see, the ijth pairing controller would see. Numerator is the gain that controller would see if all other controllers were on manual. They were not on, and so all other control inputs were fixed. This would be the gain, denominator would be the gain that the same pairing would see, the same ijth pairing controller would see if all other controllers were on. That is, all other controllers on. That means, and this corresponds to all other controllers off. Yeah. Now imagine if lambda ij is of the order of 1. If it is of the order of 1, what that means is this particular ijth pairing, it doesn't matter whether the other loops are on or off. The gain that this pairing sees remains constant regardless of what is the state of the other loops, whether they are switched on or switched off, whether they are on automatic or on manual. Imagine a situation where this lambda ij is less than 0. That means it's negative. What that means is, depending on whether all other loops are on or off, the gain that this controller sees switches sign. So for example, when all other controllers are off, if I increase steam, temperature increases. So the numerator is positive. Now if the relative gain is less than 0, what that means is if all other controllers are now switched on, now when I increase the steam, the temperature will decrease. That's very counterintuitive. In fact, now negative feedback will become positive feedback, and positive feedback systems usually turn out to be unstable. Okay, so there is a clear issue. This implies gain sign loop, gain sign flips depending on whether other loops are on or off. Whether other loops are on or off. So this is a strict no. So avoid such pairings. What about this guy? When you got the relative gain close to 1, that means whether the other loops are on or off, it doesn't really matter. The loop says pretty much the same, that particular pairing sees pretty much the same gain. So prefer such pairings. By the way, in Niederlinsky index also I'd like to point out, if the Niederlinsky index is 1, if the Niederlinsky index is 1, I mean if this guy goes to 1, let us say, if this guy is 1, what does that mean? That means K12 or K21 is 0. That means the interaction is, there is no interaction. The interaction loop is not there. Yeah, so Niederlinsky indices close to 1 are also very good, implying negligible interaction. Similarly, relative gains close to 1 are preferred because that implies the state of the other loops, whether they are on or off, doesn't affect the gain of the ijth pairing loop. Okay. Now how do you calculate the relative gain? So when you calculate the relative gains for all the elements, all the ij elements, I going from 1 to n and j going from 1 to n, you get the relative gain array. Okay. How do you get the relative gain array? Well, like I said, lambda ij is equal to dou yi by dou uj, uk not equal to I are fixed, and dou yi by dou uj yk j not k not equal to j, k not equal to I. Okay. So what is this guy? This is nothing but the open loop, the process transfer function or whatever, process gain. This is kij. What about this guy? So if I look at y1, y2, yi, yn. This is going to be k11, k1j, k1n, k21, k22, k2j, k2n, ki1, ki2, kij, kin, and keep going, kn1, kn2, knj, knn, and you got your u1, u2, uj, un. So obviously, if all other u's are fixed, change in yi. So if all u1, u2, all these other terms are 0 except uj exists, uj is finite, everything, all u1, u2, un are 0, then you will see that y1, y2 can change, but the change in yi is equal to kij times uj. Yeah, okay. So the numerator is kij. That's all right. What about the denominator? For the denominator, we'll have to, now we want to keep the y's fixed. So u's are changed appropriately so that the y's remain fixed, other y's remain fixed. So we'll have to invert this matrix, and after we have inverted the matrix, what we will get is, so if you multiply by k inverse both sides, then what you will get is, oh boy, do I have the space to write it? I don't know, we'll see. What we will then get is u1, u2, uj, un, this vector, and let me just call the inverse matrix elements as k prime, is going to be k ki jagah I, j, k, l, m. Well, we'll just keep it k. K prime 1 1, k prime 1 2, k prime 1 I, k prime 1 n. This guy would be k2 1 prime, k2 2 prime, k2 I prime, k2 n prime. Keep going. uj is going to come by kj 1 prime, kj 2 prime, kj I prime times kj n prime, and kn 1 prime, kn 2 prime, kn I prime, kn n prime. And here what we have is y1, y2, yi, yn. Now if yi is non-zero, but y1, y2, yn are all 0, then uj will be equal to k prime ji times yi, and therefore uj by yi is going to be k prime ji. Yeah, therefore this guy is going to be, so this guy is k ij, and this guy is of the inverse matrix the jith term. Now because this is jith, what that means, sorry, this is actually 1 by, because it is, okay, yeah, okay, so therefore lambda ij is going to be k ij times k prime ji. That's what lambda ij is, where k prime is the elements of the inverse matrix, k inverse matrix. This is the k matrix, the inverse of this matrix, and therefore the relative gain array lambda is obtained by simply element by element multiplication. This is also called the Hadamard product. Element by element multiplication of k inverse, and because this has become ji, you'll have to take a transpose of that. That's how you get the relative gain array. And once you have the relative gain array, if it's a 3 by 3 system, you'll have the relative gain array will have 9 elements, and then what you do is you look for those elements that are closer to 1 and prefer those pairings. And one of the properties of the relative gain is that the sum of the columns is 1. There are other properties, but it doesn't matter as long as you can calculate it. The pairings will become obvious when you look at the elements, so you just look for those elements that are closest to 1. Those are the pairings that have the least interaction. Okay, so I think that's enough for this lecture. What we have done is looked at the Niederlinsky index and the relative gain array. Niederlinsky index is obtained as determinant of k for the particular suggested pairing divided by product of the diagonal elements for that pairing, and if this is less than 0 implies guaranteed instability or integral instability. You could still control with using that pairing one of the, you could use a p controller, and then you're not wanting all of the y's to return to set point, and then you're just fine. Relative gain array, well, relative gain array, like I said, we obtained by multiplying element by element the elements of the gain matrix and k inverse transpose matrix, and here we prefer ij pairings such that lambda ij is close to 1. Prefer these pairings. Avoid just like here, avoid. Yeah, so that's the summary of today's lecture. We have looked at interaction metrics. Next time onwards, in the next lecture, we'll look at tuning a decentralized control system, multivariable control system. So thank you for your attention. Hope to see you again next time. Thank you and goodbye. Bye bye.